And my group members are Courtney Lanner and I'm Jennifer Ross, and we're from UMass Amherst. So just to give you some background about Planck's constant, which is also known as H, it had to be evoked originally in order to explain black body radiation. So the spectrum didn't make sense with current theories. Electromagnetic waves were actually quantized, and so H became the variable that they came up with. It was able to also start to explain some other things that nobody understood, such as the photoelectric effect. That's what I'm going to talk to you about today, so that we've seen it already in quantum mechanics. And anyone who's been studying optics may have seen it for the photon energy, so we know that light is quantized. What's really great, though, is that for all of these theories where quantum mechanics comes into play, as you go to the limit of H approaching 0, you retain classical mechanics. And we know that there's a currently accepted value of 6.62 times 10 to the minus 34 joule seconds. So that's the units for H. And you can get those units from this equation here. I think this one's the easiest because I know that E has units of joules, and I know that frequency has units of hertz, which is per seconds. And so that means that H must have units of joule seconds. This uncertainty here is basically, our uncertainty is only occurring on these last two numbers, the 5 and the 7 minutes. So how are we going to measure H just in our lab? So the way that we're going to do it is by using the photoelectric effect. What happens in this system is you have a material. It's a metal because we want it to have some free electrons, the ones that are usually flowing to make the current. And those free electrons, we want those to be able to kind of come off. And the way they're going to come off is because a high energy photon is going to hit the metal, and it's going to basically eject a photon off of it. And so, basically the photon, as we saw in the last slide, has an energy. So the E equals HF. And then the electron will come off with an ejected energy, which is its kinetic energy plus this is like a potential energy. And so what is that potential energy? It's actually, we call it the work function. So this is the energy that it takes for the electron to be bound to the metal, to be part of this kind of many electron system. And when you hit it with a high enough energy photon coming in, then it's able to eject that electron off. And it's kind of like conservation of energy. I think it's exactly like conservation of energy. So the energy going in is the energy going out. And so, and this value is going to depend on the metal and the surface condition. And this is important. We need to have this this energy of the photon that we're putting in. It must be greater than that binding energy. We have to like overcome it. That's kind of why it's like a potential energy. So we have to be able to overcome that. And then any extra energy that comes along will all be in the velocity, the kinetic energy of the electron going out. So as I just said in the last one, the energy going in is going to equal the energy coming out. So that's why we're going to have energy conservation. And so this is the main equation that we're going to use. And again, this kinetic energy that we're going out, we want to be able to measure it. And so the way we're going to do that is by using this apparatus. So let me explain this apparatus first. So this apparatus is just a simple circuit. We have a variable voltage that we can change here. And then it goes through an ammeter, so we can measure the current that's going across. And this is basically a capacitor. So it's like you have like two pieces that are spaced apart, and it's actually in a vacuum, so our system actually has a vacuum around it. And the metal we're going to use is a piece of sodium, and so it's all in this vacuum tube. And then it's in glass though, so we can shine light onto the sample. And if we shine light bright enough, then we should be able to eject these electrons. When the electrons fly off and hit the other plate, then we'll get a current, right? Because so normally we don't want to have a current, but when we shine a light, we should have a current going through, right? And so then, because that'll complete the circuit. And then what we'll be able to do is measure the current. But that's actually not all that we want to do, because we can actually, this potential that we apply can actually fight against that current. So we can actually try to suck the electrons back onto the sodium metal here. And so what we're trying to do is, so if we can, it's called a bias, like you're biasing the potential. And so let me go to the next one because that'll help. Okay, so we're going to apply a voltage which is opposing this electron from going this way. It's going to try to make the electron go backwards. If we have a positive voltage, that will actually help the electron go forward. But if we have zero voltage, there's some amount, so we're not applying anything here, just a closed circuit, then there's some current that we'll get just from the photoelectric effect. But then what we can do is we can actually apply a negative voltage, and that will then now oppose it from wanting to go off. And so then we'll get a current, our current will drop because of that, because we're pushing it the other way. And then as soon as we get to the position where whatever the voltage is that we apply, we get a zero current, then that's what we're going to call our V stop. So that's going to be the voltage that we're going to stop the current from occurring. So it's not that the photoelectric effect has stopped, it's just that we're no longer, we're kind of not we're biasing it so that it can't release because there's an extra potential on it holding it on. It's like we're increasing the binding in a sense. Okay, so and so if no photoelectrons are detected there, then we know that this amount of, again, we're doing kind of a conservation of energy here, so the kinetic energy max is going to be equal to that voltage times the electric charge of the electron. Then so we're making these measurements, and so we can actually change the frequency of the light that we're putting on. So this down here is the frequency of the light that we're using. And then for each frequency of the light here, HF, it'll actually have a different voltage stop, which is here. So actually just bring this HF down. And so we now have a different stop voltage for each one. And that's because, again, the frequency is proportional to the energy, so we can overcome that. Okay, yes. And so if I now take this, again, bring this down, HF equals E times V stop plus phi, which is, again, remember, it's the work function. I can resolve this for V stop. And so now I have a function which is V stop as a function of the frequency of the light that I'm using. And now you can see that this is mx plus b. But the slope of that line is actually going to give us h over e. And you can see that the slope has units of voltage times seconds. And if we divided that by coulombs, then if we multiply it by coulombs, then we'll have h by itself. Measure this, and we can measure that slope. And then the other thing with this that we can get from our fit, so we can do a line fit with two unknowns. The slope is one, and the other one is the intercept. And so this is actually going to intercept down here in a negative, and then from that we can actually determine the work function. So we need different frequencies of light in order to make this measurement properly, and so we actually in the lab have 5 different lasers or light sources that we can use. And so we can use a helium-cadmium laser, which is in the UV. We can use an argon, which has 2 different lines. That's one that's a violet and one that's a blue. It has 3, and also a green. And then a helium neon laser, which is red. And you can see that then there's different frequencies that we can achieve. So calculating the slope, so using all of this together, different frequencies of light, measuring V stop for each frequency, then plotting that, fitting that with a line, finding that slope, this is that slope, and then multiplying that by E, which is the charge of an electron, then that will be able to give us H. Our uncertainties, so how good can we measure it? So again, our uncertainties are going to come from different places. So obviously, the measurement of the charge on the electron has uncertainty, but it's really good. So it's like 10 to the minus 7 of the original measurement. So it's 10 to the minus 19, 26 coulombs. So 10 to the minus 26 coulombs is our error. So that's pretty small. And it's negligible compared to some of our other errors. So the next smallest error is actually this one here. I should probably put these in a different order. The typical laser, so even though we say it's at one wavelength, it actually has a width of the wavelengths that it actually is emitting. And so from those widths, we actually know that there's 10 to the minus 8, but that's also really small, so it's also negligible. There's some error from our fitting to in our plot, and this is where most of the uncertainty comes. And there's also some uncertainty in our ability to actually find v-stop. That actually has to do with how well you can set the voltage across and where is zero. We actually did some preliminary experiments on it, and we found that we could estimate how well getting to the voltage with 0.1 volts. And then if you compile all of this together, then that gives us an error on our slope that is about 1% error. So, and that would give us an error on H of about 1%. Interestingly, we can also calculate this work function from our plot, and yet that does not come into our error for H because it's a separate thing. In conclusion, Planck's constant will be measured with an uncertainty of 1%. We are able, by using this experiment, to verify the photoelectric effect, and we can also measure the work function of the metal that we're using. There are ways that we can make improvements to this measurement. For instance, we could use light sources with a larger frequency. We could use white light that has a lot of different wavelengths, and we could use diffraction grading in order to select different wavelengths. We could also measure this work function versus temperature. So that's it. So if you have any questions, I'd be happy to answer.
Jenny, can I ask a question about the accepted value?
Yes.
Do you know how that's measured?
So I know I got this from NIST, and that's the National Institute of Standards and Technologies, but I don't know how they do it. But I will definitely look that up because I agree that that's something we should probably talk about, especially in our manuscript and in our final presentation.
So today I'm going to give my initial presentation on Planck's constant from the photoelectric effect. And this is an experiment that Jenny Ross and I are doing, and we're in the UMass University. So we'll start with the significance of H and the accepted values of H. So what is H and what do we think it is? And then I'll talk about theory, and then the experimental methods, so the apparatus and the procedure, so methods, and error, and then there will be a conclusion where we'll talk about some stuff. So today I'm going to talk about Planck's constant and how you would measure it with a photoelectric effect, and here's my outline. So Planck's constant H. The development of quantum mechanics began with Planck's constant H, which was invoked by Planck to explain black body radiation spectrum and quantization of electromagnetic waves. And the same value of H explained the photoelectric effect. There is a continuing role in physics and technology for Planck's constant H. The photon energy is E equals HF, and the conductance quantum is 2 E squared over H, and the uncertainty principle says, I can't read that because the font didn't show. The limit H times 0 gives classical mechanics from quantum mechanics. Currently accepted value is this. And the photoelectric effect is the emission of electrons called photoelectrons from a surface when light is shown on it. It was first observed by Alexander Edmund Becquerel in 1839, although credit is usually reserved for Heinrich Hertz, who published the first thorough investigation in 1880. So Planck's constant is really important. Here's all the reasons why it's really important. There are lots of things that you do with Planck's constant. It's really important for physics and quantum mechanics and even classical plasma mechanics, so that's kind of interesting. And then we're gonna study it with the photoelectric effect, which was done a pretty long time ago, but Einstein's 1905 paper on the photoelectric effect is one of the things that he actually got the Nobel Prize for, which you might not know because he didn't get it for relativity. But lots of people think he did, but he didn't. And yeah, so that's what we're gonna do. So our experimental methods involve like this apparatus, and so you can see there's like light, and there's this circuit, and then that's a photoelectron. So the equations we're going to use are HF equals KE plus phi, and KE equals EV stop. And the graph is going to look like this. It's going to be current and voltage, and it's going to go like that. So what was this slide? Sorry, this didn't show up so good on, I don't remember what this axis is. But I think we're gonna plot our data like this, and then like you get H from the slope. So some more stuff about experimental methods, like there's going to be a photon frequency, and you can see that there's like different sources, and
I can't hear you.
oh, so there I was saying that we have, one of our methods is that we have to have different sources, and these are the sources, and then there's
I can't.
there's different frequencies, and these are, it's not really important. So yeah, so this is how we're gonna get our H. We're gonna take the slope back on that other slide. Where the other slide? Oh, so the slope here. There's gonna be a slope, and then we're like gonna take a slope and we're gonna multiply it by this thing. And so this is the value that we should get. So in conclusion, Planck's constant will be measured with experimental error. We will prove Einstein's theory of the photoelectric effect is correct. The work function of metal will be measured. Thanks.
And I'm seeing that you have an accepted value.
Yeah, that's right here.
Okay, I just have a couple of questions about that. So, do you have units? Do you know what the units are?
Oh, I don't think each has units.
I think it does. You have a couple of equations. Maybe you could figure out what the units are from those equations.
So the conductance quantum, let's see, E has units of coulombs, and, but I don't know what units conductance has. Okay, let me, well, how about, okay, so energy equals HF. So energy has units of ergs, then frequency has units of like seconds. So if it'll be like an erg per second, erg times a second. Is that right?
No, not it. What else do we know about
whatever.
frequency?
I just, yeah, sure. So what are the units of frequency? Okay. Okay.
Okay, so let's think about frequency. Hertz. Have you heard of Hertz before?
Yeah, like the Frank Hertz experiment?
Anyway, frequencies in per seconds.
Per second.
So what does that mean? Is it seconds or?
Well, maybe, so like if I had energy over here and I had per seconds over here, then I guess I would get energy per second.
Yeah, and what do we usually measure energy in? We don't usually use ergs, right?
Oh, yeah, what's the other one?
Joules.
Oh yeah, joules.
Joules. Okay, so, all right. So what do you think?
Okay.
So what are the units for each?
Yeah, so it's like joules, and then over here we've got like per second, so it's like joules per So maybe I'll go to the board.
Yeah, go to the board.
So I've got like it's a joule second.
Yes, it's a joule second.
JS. It's a JS.
Excellent.
Yeah, JS.
Okay, so
JS should be there, and that's just a typo. I'm sorry.
Okay. You have this this very long number times 10 to the minus 34, and you have this number in parentheses 29. What does that mean?
So I think that's like the percent error.
You seem to have a lot of references in here that I'm seeing.
Yeah.
But you didn't. I'm not seeing any. It's not clear where those are referencing to.
Oh yeah. So so these are like the references in Wikipedia. Did I put that at the end? Oh no, I guess. Gosh, I don't know where those references are.
Yeah, we need to have references.
Oh, okay. Yeah. No. I'll do that.
Okay. You have HF is KE plus phi, but I'm not sure what KE is or what phi is. What are those?
Yeah. So so KE is like a kinetic energy. And phi is the stopping. Oh no, phi is the work function. It's the work function.
What does that mean, the work function?
It's like a property of the metal.
Okay. Do you know what it is? Like, do you know where to find it?
No, I think we're gonna measure it. I think we're gonna measure that.
You're gonna measure that? Okay.
Yeah, I think that's one. I think that's one of the things we're supposed to do.
Okay, let's go on to the next equation. The KE equals EV stop. Can you tell me what E and V stop are?
So yeah, so E is E, like the electrical constant, and so V stop is like, so that's what this graph is about. So like you've got your current and you've got your V, and so it's like when the stop, then that's, so like V stop.
Okay, so maybe it would help if we talked about the apparatus diagram, because I'm still not understanding where V and current, where are you measuring them? Is this the apparatus that you're going to use? Is this the circuit you're going to use?
Yeah. So like there's V.
Okay.
And then it's like the light and the electron. And then this is a variable power supply.
Okay, so so if you have a plot of something, right? Go back to the plot. You have V on the x-axis.
Yeah.
Where are you changing that V? What V is changing?
See, I'm changing the light. We're gonna change the light, and then like the V's gonna change.
Okay, and then the current. Can you just show me where you're gonna measure the current? And
so I guess like this electron, there's like a current in here.
Okay.
From the electron, I think, because that's the photo. I think we're measuring the photo current.
Okay.
And this whole thing has to be in a big black box because you have to keep the outside light out, and then we're gonna put the other thing in the shield.
But now you have a lot of unknowns. So like you have a V, you have an A, and you have a phi.
Yeah. I think that's where this graph. So the graph
this
is
graph,
like something and then something else, and like the slope is going to give you the H, but like the y-intercept is going to give you, or the x-intercept, one of the intercepts is going to give you something else that you need for this equation, so it'll be fine. It'll just like all work out.
Okay.
Yeah.
And so so we don't know exactly what's on the y-axis. Maybe it'd be good to either just go out, or you can make an educated guess.
So I see like 60. Let me come out of that. Oh, okay, yeah, right. So I guess this is the radiation frequency.
Yeah, what does that mean?
So it's like I don't know. I guess I should.
You said we're going to get it from the slope, but what are the units of this slope?
Oh yeah, so the units are going to be so rise over run, so it's going to be like this over this, and this is hertz, so it's going to be a volt per hertz. Yeah, so like a VS.
Yeah, so right, that's right. Is that the same units as H?
No, so, because the H is joules seconds, so, they're not?
First of all, let me just double check. That capital H, is that the same H?
I think so, yeah.
Okay, so we need to figure out, so we're looking for joules, right? We want joules seconds, and we have volt seconds.
Yes.
That's our slope. So what times volts will get us to joules? Again, think about potential energy. We talked about this earlier when we were talking about units.
So potential energy is potential times charge, so we need the charge, and the charge of the volts will give us the joules.
Okay, so what do you think that number might be?
It's a charge, that's like, that's like the electron charge.
Okay, so like just for funsies, what's the units of that?
Coulombs.
Okay, very good. Okay, so that's how you're going to get from the slope of the plot, right, to get to H. Okay.
Yes.
All right. And then we're going to try to get it close to this currently accepted value, right?
Yes, we should get that value.
Okay, so one thing I didn't see in your slides was any analysis of your uncertainty. So when you're quoting these numbers, these are uncertainties in the current best measurements.
Yes.
Okay, so but are those your uncertainties that you think you might have?
No, our equipment is really crappy, so we're not going to be that exact.
Okay, so do you
We're gonna
have
make a lot of mistakes?
Okay, wait, you're going to make a lot of mistakes?
No, but like we're not going to be able to measure stuff because the equipment is crappy.
Okay, because the equipment is crappy. So what exactly way? It's really old. Okay.
Yeah.
Do you know what your how well it can measure anything?
No.
Are,
No. I guess we'll figure that out when we do the experiment.
Okay. So one of the things you need to do on these initial presentations is to have an estimation of your uncertainties that your equipment will have. And again, remember that doesn't have anything to do with human error. If you messed up humanly, then you should just repeat the experiment, right? Okay. So I didn't see that at all here. So let's say you do calculate the uncertainty of your ability to measure. That will give you an uncertainty of your slope, correct?
Yes.
And now you also have an uncertainty from NIST on the charge of an electron, correct?
Yes.
How do you, they each have their own uncertainty. How do you find the total uncertainty of your measurement?
You take the uncertainty and the slope and you add it to the uncertainty in the constant.
Okay. What are these arrows pointing to?
I guess I'm not very good at PowerPoint. Sorry, I don't know where this came from. Yeah,
Okay, they just some randomly appeared.
Yeah,
Okay.
I guess, sorry, yeah, I'm not very good at PowerPoint.
Okay. Did your team members look this over?
So I had a really, really rough week, and so I emailed them to them last night, but did you guys look at they didn't give me any feedback on them, and I know that's probably my fault because I know I gave it to them really late, but I just had a really, really rough week.